So this is our fifth lecture, and as you remember in lesson number 3, we've talked about derivative, about slope of function, and we've really talked about how this can relate to finding minimum. And if you've done homework, you can actually discover that there are different behaviors of functions near minimums or near points where derivative is equal to 0. And because we are talking about machine learning, and machine learning involves creating huge models with a lot of parameters, that means that our functions are usually multi-derivative, multi-variable, excuse me, and that's why we need to use an extension of derivative, which is called partial derivative, which we are going to learn about today. And based on other properties of partial derivatives and functions in points of minima and maxima, we are going to create reincarnation of greedy algorithm, which work for discrete models, but now it will work only for continuous models, and it's called gradient descent. Which we are going to talk about in the second half of the lecture. So, what is a partial derivative? It's quite a complicated mathematical concept, and to understand it, let's begin with introducing 3D graph of function with two variables. So, you can see this is some function which is precisely x squared plus xy plus y squared, and it has such shape, and we need to, and we don't know how our graph changes if we change x and y a little bit to find something kind of slope, but for multi-derivative functions. So to just fit our partial derivatives into usual derivatives, let's first draw such plane, and let's just draw a 2D graph of intersect of our 3D graph and this plane. And now, after we've drawn it, we can see this graph, and actually this slope in this particular point, for example, is called a partial derivative of z with respect to x. And yeah, it's probably a geometrical meaning of partial derivative. So let me briefly re-explain this. So if we have some, first we are going to stick with 3D graphs of functions with two variables, and if our, so that's how we define some shape, and now we can draw a plane whose y coordinate will be constant. Y is equal to some y with a star, and we can just draw a plane. Remember that y coordinate is constant, and so this plane is parallel to x-axis and z-axis. And after we've done it, our graph intersects with this plane somewhere, and it creates some line. So this line is intersect between plane and a graph of this function. And now we can consider this graph as a 2D graph of a new function which can be defined as a new function, which really depends only on an x variable, because we've reduced number of parameters and chose our y parameter to be y and star. And because our plane intersects with this 3D graph, which means that all points of intersection can be found by this formula. So we've just taken points of 3D graph which are placed at y coordinate, which is equal to y star coordinate, and we've reduced number of parameters from 2 parameters to 1. And now we already know how to work with a graph with one variable, and so we already know that how to calculate slope of this line. Here we have some graph. This is our new function. Then the slope is equal to just derivative of this function in this point. So we've just we are constantly reducing number of parameters, and we just came up with reducing our partial derivative to just derivative. And what happens if we have more than 2 parameters? Then we're reducing again. For example, if we have some new function with 3 parameters, and we want to take partial derivative with respect to x, and we will denote this like that. So this is the notion of partial derivative. Then it can be rewritten as just derivative of new function which depends only on x. And this function can be defined as follows. So we've set our y and z constants, which are not main variables, and which are not variable we are taking partial derivative on. And so this means that other variables are constant, while variable we are taking partial derivative on is not constant. And in this way we've reduced number of variables to just 1, and then taken partial derivative, which is equal to just usual derivative of a usual function. So that's about geometrical meaning and how to interpret this. And if we have more than 2 parameters, it's quite hard to imagine that graph, because it will be or color graph or 4-dimensional, which we just cannot perceive. And that's why it's a good example of 2-parameter function. And if we have more than 2 variables, then we just cannot take our partial derivative by graph or geometrically. So we need to define some way of finding our partial derivative with analytical results that we've just got so far. So now I will introduce to you that actually partial derivative is taking partial derivative analytically is a quite easy task. And the main rule, if we have some function and we take partial derivatives of it, then we just consider all other variables constant, and that's it. So they don't change. That means they're just constant or some numbers which we just have not introduced in number form, which means that, for example, all constant, differential rule about constants is applied. And let's take a look at the simplest example. And this is just a multiplication of x and y. And we want to take our partial derivative with respect to x. So this can be rewritten as xy. And because we are taking partial derivative with respect to x, our y variable is just a constant, a number. We can do the same with function like that. It will be the same easy, and you already know how to take derivatives of such functions, and it will be just equal to 5. And in case of taking partial derivative of z function, if y is a constant, then we just can rearrange our constant from sign of partial derivative, and partial derivative of this variable is equal to 1. That means that if we actually build a graph of z function, 3D graph, and it will look like some kind of ball. And now if we are taking our cut with keeping our y variable constant, then we will just get that slope of this cut that we've created is equal to y coordinate at any point of x. So what we've really done, we've reintroduced our partial derivative as a derivative, where we take our function and just reduce our parameters and take all other variables as a constants. And that's the main rule, which allows you to calculate partial derivatives just like normal derivatives. Just you have to consider that other variables are just a constant, and you can do all pretty the same tasks. Now we can, for example, take another partial derivative of other function, just for example. So let our function be, for example, x plus y divided by. I've chosen this to remind you some rules of differentiation, and now we are going to apply them again in favor of partial derivatives. So now, as we take our partial derivative with respect to x, y's are constant, and now we can use rule, as you remember, its number is 5 probably, and it's called quotient rule for calculating derivatives. So, as you remember, derivative of fractions of fraction of functions is equal to derivative of first function multiplied by second minus derivative of second function multiplied by first, and all divided by second function in square. So now we've reduced our problem to just finding derivatives of this very simple, finding partial derivatives of this very simple expressions. So x plus y, and we can let's write just this partial derivative of x plus y. So again, we can use a rule of differentiation of sum. And as you remember, it's equal to 1, because if we're taking derivative of x, it's equal to 1. And derivative of y, which is equal to 0. 1. And the same goes for x minus y. And this is equal to
1.
Correct, 1, because it's just 1 minus 0. 1. So now we can rewrite our expression again and get that actually this derivative, this partial derivative with respect to x, is equal to 1 multiplied by x minus y, minus 1 multiplied by x plus y, minus x minus y. And here we go. So we've calculated partial derivative. It's not a very complex task. So just got to keep one rule. I will remind you once more that just other variables are just constants. And that's it. That's all about partial derivatives and nothing else, because that's how we calculate them analytically, and we don't actually need some other applications. Actually, we will need one more application, but it's not very hard, as you could see. Now we've got probably one of the most serious business, which partial derivative is involved to. And as you remember, in homework you needed to calculate first derivatives of some functions. Then you need to graph these functions at points which are equal or near points where derivative is equal to 0. And if you've done this right, then you could get that functions behave differently, and actually there are three main types of behavior, which function with one variable has near regions where its derivative is equal to 0. So first one. minimum behavior. So that means that near a point where derivative is equal to 0, there is a minimum, which means that this point is the largest value which you can see in this nearby region, this region. Then, of course, function can go up and down, but it doesn't really matter because oh, sorry, it's called maximum behavior. And it doesn't really matter because we only consider this small region, and that's why this maximum is called local maximum. Local maximum. The second behavior is opposite to maximum, which is called minimum. And again, we don't bother with what behavior function has outside of this region, and that's why it's called local minimum. And again, we can observe that the lowest point, derivative in this point is equal to 0. And finally, the third one, which you could observe, for example, if we consider graph of cubic function, we can see that actually derivative of this function is equal to 3x squared, and it's equal 0 only in point 0. But we don't observe non-maximum, non-minimum, it just goes up and it goes up again. And because of such behavior, it's called a saddle point. Saddle point. It's a point where derivative of function is equal to 0, but we aren't observing neither local maximum nor local minimum. And that's actually very important in machine learning, because now when we have pretty important tool, which with help of that we can understand where we have minimums and maximums, because in machine learning we optimize very much, a lot of things, and this is a very strong rule, and despite its weakness that we have saddle point behavior, it's still a very common used rule, and it's called Fermat theorem. So this rule of finding lowest or finding of maximums or minimums can be reconsidered as a mathematical theorem, which states that if x0 is minimum or maximum, then derivative of a function at this point is equal to 0. It's not like it's something opposite, because in your homework you could observe then if derivative of function is equal to 0, then we observe 3 behaviors. But this is quite opposite, and it states that if we found minimum or maximum, then derivative must be 0. And that's why we can use it, despite still that saddle points exist. We can still use it just by we can just find every point where derivative is equal to 0, and then loop through them and find which is appropriate for us, which is maximum, which is minimum, and which is just a local point, which is just a saddle point. And that goes for simple functions with one variable, and this actually works for multivariable functions too, but in a bit different form. So if we have several variable function, then if some point so this is some point in multi-dimensional coordinate space, and if it's is minimum or maximum point, then there we had derivatives of each derivatives just equal to 0, but because we have several variables, now we can use partial derivatives. Just if we have minimum or maximum point somewhere on multidimensional graph, then that means if we take a cut through this graph and view how our derivative behaves in our just simple case and one variable function, then this point will be minimum or maximum too, obviously. And that means that for each partial derivative that we take, they all must be 0. And that can be rewritten as a system of equations. And we will have that many equations as we have our variables. And that means that we actually have a system of equation with n variables, system of n equations with n variables, which means that solution can exist, but sometimes it cannot, or sometimes we can have infinitely many points of local minimum or maximum, but that means that we can actually solve it. And if we had opposingly, like for example, too many variable sets and not so many equations, then we just could not solve it. But that means that we can actually find exact points, exact numbers where a function has minimum or maximum points, or a saddle point. And now I'll show you an example for 3D graph. So that's how we took derivatives from our theorem. You can see minimum, maximum, and the saddle point for one variable function. And in multivariable we have this system of equations. And actually, because each cut of this graph, each two-dimensional graph that we take from this multi-dimensional graph can behave like a maximum, minimum, or saddle point, then there are then number of different variants of different combinations is growing. For example, we can have a saddle point and a minimum and a maximum, and that's all different combinations. And that's why mathematicians just choose to categorize all these points as if all cuts are minimums, then this is a minimum point. If all cuts are maximum point, then this is a maximum. And if all other variants, where our derivative is still equal, all derivatives are still equal to 0, it's called saddle point. And now, if we have a 3D dimensional graph, we will have precisely 6 different variants, and only 2 of them called maximum and minimum. And all other can be called as saddle points. So in this case of saddle point, we have one cut behaves like a maximum, and another cut behaves like a minimum. And there we have a saddle point plus a minimum, saddle point plus a maximum, and 2 saddle points. And you can see that there is no like minimum and maximum. We can still follow. Go, for example, if we are searching for a minimum, we already know that if we are searching for a minimum, we can take an example of a ball, which is trying to find a minimum point with minimum of potential energy. And if we take a ball here, then it will just go down, and without any momentum, it just won't come out. And if we have saddle points, then this is actually a point of where derivative is equal to 0, which means that ball can actually exist here. But even if we have a small momentum, then in that case ball will just go down and slide down in all these cases. So it's not a minimum, it's called a saddle point. And now we are going to use Fermat multivariable theorem in practice in an example which is called linear regression. Linear This is a great example of finding minimum values using partial derivatives, because it can be solved manually, because we have only two parameters, as you can see. So what linear regression is called? When scientists make their experiments, they usually have some data points. And for example, if you can observe a temperature of a ground depending on an hour, and in that case, this x-axis will be your hour, and y-axis will be temperature of a ground. Temperature. And because scientists love, especially physicists, love simplifying things because they love especially the most simplest case of dependence of a function, which is called a linear function. Just the simplest. And if you're a scientist and you got some experimental points, then you want to fit these experimental points in one line, which means that you want to find such parameters or such line which will the best fit in this data and the best correspond with this data. And then you can use parameters of this line for further experimental or theoretical research. And as you can remember, linear function can be rewritten as this formula. And what we can actually observe here, that we have one parameter and second parameter, and all other letters are just variables on our graph. Which means that if we want to find the best line, then we want to fit our two parameters, which already means that our case will be multivariable because we have two parameters. And we want to find the best parameters to fit our line. So we've defined parameters which we are going to fit, A and B. Second, what we are going to optimize, how to describe wellness of this line fitting our experimental data. And Legendre and Gauss, as I remember, in end of 18th century and at the start of 19th century, they proposed such definition of wellness. It's called square error, which means that if we have some point, then we can find this distance, y distance between line and point, and denote this like delta y, and then we can sum all these distances, which are called offsets, and but we won't be summing them by modulus. We are going to sum them by square roots, by squares, because square is a normal function, and if we are talking about modulus, then it's a pointy graph, and it doesn't have derivatives in some point. That's why we are going to use squares, and the square error will be defined as just sum delta y1 squared, delta y2 squared, and so on for all points that we've got. And finally, how to define these offsets, because we've defined them as difference of y coordinate of a line and a point. It can be easily shown that delta y is equal to y. For example, we are taking ith point, and then it's equal to that expression. So we are just subtracting y line at point where its x coordinate is equal to coordinate of a point. And now we can substitute x coordinate of a point into this linear formula and get that offset is equal to and now we are going to sum all of this. We're going now sum square offsets, and we'll get square error. And now we've got what we want to optimize. So we want our square error to be as minimum as possible. And just let's rewrite this square error in more easy way. So this is called sum. And if we are summing from point 1 to point n, it can be interpreted just like a loop in Python, but where you start your range from 1 to n inclusively, and you are summing squares of offsets, or we can rewrite them square. And now, how are we going to optimize? Because it's actually possible to draw an analytical formula, and because partial derivatives are actually analytical, approach to solve such optimization problems, then we are going to stick to partial derivatives and use multivariable Fermat's theorem to optimize our square error and to find the best line. So as you remember, Fermat's theorem states now that partial derivatives with respect to each parameter must be equal to 0. So firstly, let's take partial derivatives of parameter a, b, and then I'll just rewrite formula because we'll end up with just linear system of equation, system of linear equations. So partial derivative with respect to a is equal to partial derivative of, and now I'm going to write this again as a sum, as a normal sum, which we are common with, like y1 minus plus plus so this is whole expression, and we are taking partial derivative with respect to a. So this is a sum, and that means that we rewrite all this as a sum of partial derivatives, and I'm just gonna rewrite this as follows. And now it's much simpler to take partial derivatives because it's just a square function, and now we can use chain rule or sixth rule of differentiation, which states that derivative is equal to derivative of whole function, and this is square function, which means that its derivative will be just 2x if we've changed our denotation for, then this derivative will be equal to 2. So we are just taking this one and as this chain rule states, it multiplied by inner function, derivative of an inner function. And now we just need to take derivative of an inner function. And now y1 is just a number. Y1 and x1 are just numbers which we are going then to use, and b is another variable, but as we remember, it's a number too, or a constant. And if we are taking partial derivative with respect to a, that means that xy is a derivative of such expression will be just equal to minus x1. So partial derivative of this small piece of this whole sum will be equal to minus 2 x1 y1 and now we can all this rewrite back to our sum denotation as like that. Minus 2 and So this is our first result which we've got. And now we can do the same for b parameter, and it will be even easier because we are going to do this again. We are going to rewrite our square sum as a sum of these small squares, and I'm just gonna write one part of the sum, and then the rest will be done by analogy. So we are again taking a partial derivative from a square of this offset, and again by chain rule we've got that we firstly got our derivative of square function, which is equal to 2 multiplied by a variable, and then we are taking derivative of an inner function, and derivative of this inner function will be equal to, because this is a constant, this is a constant, a is a constant too, because we are taking partial derivative with respect to b, and which means that b is not a constant, and a derivative of minus b is equal to 0. B is variable, and derivative of variable with respect to variable is equal to -1. And again, we can rewrite this. So it's not very complex. And actually, if you know how to work with sums, and if you really want to derive this from scratch, you can do. You can get a system of 2 linear functions, which right now I'm going to show you, and I'm going to show you a solution. So that's how we can, for example, you can see that blue line is not as fit as green line for this experimental data. And here I rewrote what we've just got on a board, and if you know how to work with sums, you can simplify this a bit and get that it's actually a system of 2 linear functions with 2 variables. Here we have a, here we have b, and a. So this is just coefficients are a bit unusual because we are working with sums of points, data points, and if we solve this system, then we've got such an answer. So here we just so now we can we've got an analytical expression, which means that actually you can encode this in Python, which will be in your homework, and these sums are nothing but just loops, and you'll just need to loop through your data x and data y, got some sums, and then get your a and b parameters, which are going to fit the best. This is your homework, and also you've got another optimization problem, which considers that you have a box and you have its sides are equal to x, y, and z, and you've given that box have a whole area area of this box is equal to S. Area is equal to sums of these six faces of a box, and you need to optimize volume or find a box with such parameters of x, y, and z, where volume of this box will be maximum. And you also need to find this volume depending on total surface of this box. And answer can be obvious right now, but you'll need to solve it using Fermat multivariable problem. And I think that's it, and we're doing a bit break, and then we are going to talk about gradient descent.